So for our exciting second part of 1.4, it would be cool if it was the last part, but I don't think it will be. We'll see. We'll just see how big a nerd you are. We'll see. Alrighty, so we already know what a relative or local maximum or minimum is. A maximum, wait, what's happening to me? I'll be okay. A relative or local extrema, that just means it is a maximum or it is a minimum, but it's not necessarily the largest, necessarily the smallest. Y values on the graph of a function where the function changes from increasing to decreasing and vice versa. And we were more specific about that. We said if you are going up, then down, you found a maximum. So increase to decrease is a maximum. Decrease to increase is a minimum. Global or absolute, that means the highest or the lowest. The highest or lowest y values on the graph of a function or on a specific domain of a function. Why does it say or on a specific domain of a function? Well, because sometimes we have endpoints, and endpoints can represent extrema as well. So for these first examples, very simple. It says in the graphs below, label and identify relative and global extrema for each function. We're literally just going to put a dot there and say, you know, local min-max or absolute min-max. What feels like good colors? Orange and blue feels like good colors because go Gators, okay? Let's see here. Right here, we do have a maximum. Because of this arrow, would this be an absolute maximum or a local maximum? Local. This graph has no absolute, also known as global maximum, because it points up forever. So this is a local max at the coordinates of 1, 5. And same logic. Because there's an arrow pointing down, this graph does not have a lowest point. But it does have one right here that is a low point in this tiny neighborhood. So using the same logic, we could say this is a local minimum at 3, 1. So it should be pretty easy to identify if they land on pretty places. This next one, I see 2 maximums. This one happens to be overall the highest point on the graph though. So even though they're both local maximums, this one is a global or absolute maximum, whichever terminology you want to use, because it's the highest point that this graph can actually reach. I'll say global, just because I don't feel like spelling absolute. Global max. Its coordinates are 2, 8. And the other one, yes, it is a maximum at -3, 0, but it's a local max. I'm not even going to write the word local. There's a valley right there, a low point in the general neighborhood at -1, -2. So would this be local or global, class? Local. The reason why it's local is because this graph points down forever. So yeah, we have a local minimum right here. What did I say? -2, no, -1, -2? Okay. Boop. 2 more times. Here's a maximum. I guess if we want to, we're going to have to estimate that max, aren't we? Looks at what, 3.5, 9. Arrows. So this cannot be global. This thing goes up forever. So local max. What did I say? 3, 5, 9. And arrow goes down forever. This cannot be a global extrema. So it's a local minimum at -2, -11. Easy peasy. Do we need to do the fourth one, or do we get it? It's kind of obvious, right? Okay. I'll just say it. Global minimum right there. Local minimum right there. Local maximum right there. I'll just say it. So we have a key concept down here involving the degree of the polynomial, and if you flip back to the very beginning, the degree of the polynomial will be the largest exponent, and if it's written in standard form, that largest exponent will end up on the leading term right in the front, right? And I am going to come back and I'm going to write something on this page here in a few minutes, but degree of the polynomial, that is going to be the highest exponent. A key concept that says polynomial functions of an even degree. So we're talking about polynomials of 2, 4, 6, 8, 10, 12 degree. Will either have a global maximum or a global minimum. Interesting. If you come up here and look at these two pictures, the two that had global extrema were this one and this one. So why is it true that even degree polynomials will always have a global extreme value? Anybody want to take a stab at it using those two images?
Because like a quadratic is like a U shape and it has like a vertex, and like all the even polynomials are like a U shape.
So Barry says they're all somewhat U-shaped if they're even degree polynomials. It's not so much that they're U-shaped, but they could be, but specifically it's the endings, right? So you could imagine they're U-shaped between their endings, right? Even degree polynomials, the two endings always point the same direction. That means they will have a lowest point, or they will have a highest point. This one has a lowest, this one has a highest. So why? This is because the endings point the same direction. So if even degree polynomials have our endings point in the same direction, what does that tell you about odd degree polynomials? Olivia says opposite directions. So what does that mean for global extrema then for odd polynomials? They'll only have locals. So odd degree polynomials will, as long as they're continuous, with arrows on the end, odd degree polynomials will never have global extreme values, only local. Interesting. See, that's an understanding style thing where it could be a test question and you do absolutely no math. You just understand that idea. So because the endings will always point the same direction for even degree polynomials, they will always have a global extreme value. Now, it might be the exact same value just happening twice. Like this one. This is the global maximum. It just happens in two different places. That's okay. That's all right. So let's flip it over. We're going to utilize our graphing technology for this page. It says using graphing utility to determine the absolute or relative extrema for each function shown round to the nearest tenth when necessary. That's interesting, round to the nearest tenth. AP usually has us round to the 3 decimals always, but the direction said 1 decimal, so we'll go to 1 decimal. But I want to write a little bit here. Even degree polynomials, endings point same direction. So for a set of words, we can do like this. Let's draw pictures. We can either have 2 up or we can have 2 down. That's the end behavior for even degree polynomials. Here you go, 4th degree polynomial, that's an even number. The 2 endings point in the same direction. Here's a 2nd degree polynomial, that's an even number. Endings point the same direction. Alrighty. Then let us find these 3 extreme values. This one is global. Go to y equals and type this bad boy. So x raised to the 4th minus 3x raised to the 3rd plus 4x. I'm going to hit zoom 6 which is the standard window, because I'm hoping that my graph will fit. It fit. All right. It fit. We don't need to find the zeros this time. We've already done that. It was in yesterday's video. Let's go ahead and find the extreme values. Start on the left and make our way right. So the left one is a minimum. Second trace minimum is a 3. It says go to the left of the minimum. That's to the left of it. Go to the right of the minimum. That's to the right of it. Go somewhere in between the two things you just clicked on and click one more time. And we were told to round to the nearest tenth. So negative 0.6 comma negative 1.6.
I got a question.
Yeah.
How do you make like your calculators act like your normal coordinates?
Zoom 6.
Oh, okay.
Because Zoom 6 is the standard window. Okay? And it'll always regraph the moment you change the window. So we negative 0.6 comma negative 1.6. And this one is our global min. Second trace. She's explaining. I don't want to interrupt her while she explains what's going on. All right, anyway, unpause the video. Second trace, let's do the other minimum because, well, we already did minimums. So I'm going to go all the way over, to the left, to the right, and in the middle. Hitting enter at every... This is interesting. So this calculator is showing repeating 9s. Do you know what 0.9 repeating is? Well, not 1.9, just 0.9 repeating in general. It's 1. 0.9 repeating is 1. So 1.9 repeating is 2. So this is actually 2 comma, oh, that's really interesting. That's scientific notation. It's telling you there are 10 zeros in front of that 2. So it goes 0.0000000000002. So what does that mean? It's 0. This is scientific notation. It's got a negative exponent. So this number is 0. This number is 2. That's what that is. That says 2.42 times 10 to the negative 11. It's essentially 0, yeah. So this is occurring at 2, comma 0.
I got 1.74.
Right here?
Yeah.
But it said the times 10 to the negative 11, right?
Yeah.
Okay, it's still 0. It's still 0. Because, okay, so second trace min, left, right, enter. You see, it gave me a slightly different number that time. This is still interpreted as 0 because that is a negative exponent. This is 5 times 10 to the negative 11. You ever seen a 1 with 11 zeros after it? That's essentially 100 billion. So it's telling you, divide this number by 100 billion. That's what it's telling you. It's essentially 0. And this time you see it says 2.0000009. The interpretation of that is the number 2. So let's hear the real question in the crowd. It's got to be out there. Somebody already kind of did, but they asked it to somebody else. No, you just write it like that. It's 2 comma 0. Landon?
If it's writing as 0, it's not 0, would that be a,
So this happens to be one of its solutions. X equals 2 is one of the solutions. The real question is, if the minimum is happening at 2 comma 0, why didn't it just say 2 comma 0? Why is it giving me scientific notation instead of 0? Logan? Right, but no, but if you move the cursor though, it is no longer using the trace. See, I moved the cursor? I did it plenty of times. My point is, depending on how you do it, it might give you slightly different answers. The interpretation is still 2 comma 0. The real question is, why didn't it say perfectly 2 comma 0? Some of your calculators might have, and that's because you got lucky on where you picked your left, right, center. So why does it look like that? It's because this calculator is doing some extremely upper level college mathematics to estimate where that minimum is. It's not actually doing the calculus to tell me exactly where the minimum is. It's doing some very upper level mathematics. If you ever take Calc 2, you'll learn about it. It's called Taylor series approximations. It's Taylor series approximations is what it's called. It's named after the mathematician Taylor. That's his last name. Okay. The calculator did a bunch of number crunching. And the answer that it got using its approximation was so close to 2, but not exactly 2, that it had to list it like that. You interpret that as a 2. And anytime you see scientific notation with a gigantic negative exponent, the interpretation is that's a 0. Okay? Yes, Barry?
Something's wrong with my calculator.
Why?
It just says error window range.
Error window range. Did you change something?
I don't think so.
Did you try to do the maximum? Shh, it's an awful lot of noise in here. Did you attempt to do the maximum?
I mean, I just like changed, I think, like what the X is. The X max.
So you tried to go to the maximum. So second trace maximum. And more than likely what happened was you didn't click between your left and your right. Or you had your left and right out of order. Or you clicked right on the same line as your left or your right. That's what that is. So left, right, between.
It's not letting me do second trace.
Let me see your calculator. Let's see it. Let's see it. Window range. Zoom. So quit. Zoom 6. Something about your window changed. Second trace maximum. There you go. Something about your window changed and it didn't like it. Anyway, we got a maximum at 0.8 comma 2.1. Yeah, you have to round. It says round to the nearest tenth, so that's 1 decimal. Now this one. This is a quadratic. Its vertex happens at negative b over 2a. So that'll be exactly x equals 2. But what is the y value there? Well, I'm not really sure. Go to y equals, clear it. I mean, I could find it. Negative x squared plus 4x. You know, I'm still on Zoom 6, so I hit graph. We've done a little bit of mathematics, so we know that it's going to hit at perfectly x equals 2. You could plug 2 in, or you could do second trace maximum, or even cooler, you could do second table, and you can go right here to x equals 2, and you'll get your y value of 4. I'm teaching you all of this.
How does the calculator know all this?
The calculator was programmed by some very intelligent people. Mathematicians did the work, and then they told the programmers, here's what we need it to do, and the programmers made it do that stuff.
I didn't know it was X equals 2.
I did negative 4 over negative 2. I did negative b over 2a in my head. You know another way that you could have known that it was there? If you went to second table, You know on the left side it's increasing, right? And on the right side it's decreasing. So look at your y values. Look where they stop increasing and then start decreasing. See how to the left and right, above and below this 4, the digits are exactly the same? That tells you that was the vertex. It didn't have a choice.
How do you get to the table?
Second graph. A minute ago, though, Landon, he made a statement. Do you remember what you said right when I said, let's do this quadratic? You didn't say it very loudly. You said it only has one extrema. I'm pretty sure you said that. Yeah. So you notice that this quadratic, which is a degree 2 polynomial, only has one extreme value. And this is a 4th degree polynomial, and it happens to have 3 extrema. It's almost like we should be able to make a statement that connects the degree of the polynomial to the number of extreme values that it could have. Would anybody like to make a prediction? One less than the degree. So if you would please, come back to the front of these notes where it says the degree of the polynomial. See if the degree is n. There are at most n minus 1 turning points. So for degree n polynomials, there are at most n minus 1 turning points. So are we guaranteed to have n minus 1 turning points? No, we are not. For example, before I go do those examples real quick, look, y equals x raised to the 4th. When I hit graph, it gives me something that looks like a parabola. Now, it's not a parabola. It is still considered a quadratic. All even degree polynomials are technically quadratic. You don't have to know that. But it's not a parabola. You'll see it's flatter on the bottom, right? It has 1 turning point, not 3. So we don't say there are always n minus 1. We say there's at most n minus 1. Cool? Okay. Now let's go back here, and we can find these turning points. Let's do one more because I think you get it. Let's go ahead and do this one here. Y equals x cubed minus 2x. And we hit graph. Now this one happens to have really nice zeros. Well, that's not true. I guess they're not nice, are they? They're plus or minus the square root of 2. Luckily, we didn't need to find the zeros. Second trace maximum. Let's do the one on the left. Go to the left. Go to the right. Go in between. A maximum at negative 0.8, comma 1.1. Notice, please, that this graph looks to be that it is symmetric around the origin. Does anybody remember the vocabulary word for that kind of function from Algebra 2? An O. This is an odd function. What that means is that minimum will be at positive 0.8, comma negative 1.1. Second trace minimum. I said minimum. Positive 0.8, comma negative 1.1. Why does that work? I know this is a review from Algebra 2. We haven't done symmetry yet this year, have we? We will very soon, if we haven't done it yet. For odd functions, making the x value negative has the same result as making the y value negative. So if you change the symbol on this x, you have to change the symbol on the y. How did I recognize it as odd before the picture was graphed? Because every term has an x with an odd exponent on it. That makes a polynomial odd. That's guaranteed odd function when every term has an x and every exponent is odd of a polynomial. Guaranteed it's odd. If every term has an x with an even exponent, guaranteed to be even. And you don't even need every term to have an x. So if your polynomial, like if your polynomial, if every x has an even exponent, even degree polynomial. For odd polynomials, you need every term to have an x and you need the exponent to be odd. Now all that's review and patterns that I've recognized throughout the years, so if you don't know it, it's okay, it's not a big deal. Since we're just doing second trace max and min, can we skip over this one? Oh, you know what I forgot to write though? The endings. You have two options. Your options are left down, right up, or left up, right down. Don't worry, I'll bring it back. This quadratic has both endings pointing down. What part of its equation guaranteed me that was going to happen before I graph it? Well, I didn't mean the two going the same way. The two going the same way is because of the exponent, yes. But the negative is how I knew they were going down. So if the front number had been positive, they would have been going up. You see, negative people frown and positive people smile. Now for odds. Average rate of change. We've been talking about that all year, right? If you tried to connect my two arrows with a straight line, would its average rate of change be positive or negative? That one would be positive. So would this one. Begins with a positive number. This one, if I try to connect my endings with a straight line, that average rate of change would be negative. That one has a negative number on the front. So that's how you know which way your endings point. Okay? Should have learned all that in Algebra 2. Just rehashing it though. I don't know. Whatever. I just follow the directions of the homework. I'm just doing that for good notes, for good review. Okay? Now, we can actually do part 4b. We can start part 4b at least. So part 4a was about turning points and extrema. 4b is talking about the concavity again. Now, yesterday, Barry was like, hey, if I see a local minimum, will that always be in a zone of positive concavity? Yes. And if I see, which is concave up, and if I see a local maximum, is that always in a zone of concave down? Yes. That's this part of the notes. Okay. A function is blank on an open interval if the graph looks like a U or a part of a smile. Concave up. It says shade the graph at right in green for concave up. So I'm going to grab my green colored pencil that I sharpened right. See, it is prison shank sharp that I got ready for this class period right before you guys got here. And let's shade concave up zone. Prison shank sharp, that's what I said. Now here's the question. Where does it stop being concave up and start being concave down? Well, we don't really know. So we'll just do our best. That's pretty good. This green really didn't show up very well under the camera, did it? It's kind of hard to see. Best laid plans of mice and men. Green pin it is. Here, I tried to be cute. Sharpen a colored pencil. There. A graph is then concave down if it looks like an upside down U or a frown. It says shade that in blue. And since the green color pencil didn't work, I'm going to assume the blue color pencil is not going to work, and I'm just going to use blue pen. So this zone would be concave down. And remember, we estimated where the two zones, where they changed places. a function has an inflection point. At C, which is some number, if the graph changes concavity. So it says draw an estimate for this point C. So we'll go right there and say that was point C. So we were able to make a statement about the number of maximum number of term points of a polynomial based on its degree. So thinking ahead, you might be wondering, can you also do that for concavity? Actually, you can. Will we be able to do it this year? I don't think so. But with calculus, you definitely can. But I was just trying to say, if you were already wondering, thinking ahead, yes, there are ways to do that, but I think it might take a little bit of calculus, okay? Boop. I could be wrong, though. We might be able to get one of you to make a statement about it. Let's find out. It says, can you determine how many points of inflection occur in the graph shown below? Label the approximate location of each point of inflection. I'll do it in red again. Where do you think we have one? What x value do you think we might have a point of inflection?
-1/2.
-1/2 is a pretty good guess. Because -1 might be too far. So I'd say, yeah, -1/2 feels like a good guess. Let's say there's one there. At x equals -1/2. Where else might we have one? Somebody else can say a number. It's okay to be wrong, but it's not okay to... Yeah, Logan? You're not Logan, are you? No, you are. You're not, no. Landon. They both start with L's. You guys are confusing me. Anyway, Landon, sorry. X equals 2 and change. Yeah. Let's make life easy. Let's just say it's a 2. It probably isn't. Let's just make our lives easy and say it's right there. Okay, well, based on the knowledge that we had before, this thing having 3 turning points, what would be a good guess at the degree of this polynomial that has 3 turning points? 4, right? Is it guaranteed? Absolutely not. But that's a good guess. It's a good guess. So if this were a 4th degree polynomial, then it having 2 inflection points could tell you that you could use the degree, right? What might you need to do the degree to find the maximum number of inflection points of a polynomial? Hey, get a new volunteer. One of my ladies, maybe. Olivia, do you want to take a stab at it? You said the maximum number of turning points was n-1, so what do you think the maximum number of inflection points is? n-2. Yes, that is the maximum number of inflection points. Of course, in order for n-2 to have occurred, you needed to have n-1 turning points, right? So yeah, there is a way of doing it. How do you guarantee how many there are? Calculus. Just like how do you guarantee how many turning points there are? Calculus. But there are at most n-1 turning points, at most n-2 inflection points. You know what? F it. Let's put it on there. I don't know if it's ever going to come up, but man, is it good knowledge. Let's put it on there. Yeah. Feels good. Can I go back to the examples? Everybody's cool? I don't want to change if people are still copying me. Okay. Let's skip the, oh, we already skipped that. Next page. Okay. It says, well, we have to shade. Shade the concave up and concave down intervals in different colors. So I'll do up in green again. It's kind of stupid at this point because we just did that. But up in green. There's up. Down I did in blue in the previous example because the directions told me to. So there it is. Ta-da. So there are 3 ways that you can identify that a point of inflection has occurred. Don't worry, AP Precalculus will never make you estimate the value, okay? At least not on the exam, not the AP exam. I'm telling you though, what we do when we can is find the average between a maximum and minimum, you know, like go halfway between the two. But you won't be tested on that on the AP exam, so don't panic. So what are the 3 ways that we can use to identify an inflection point? Way number 1 is a 0 that is a solution to an x-intercept, a root. All these words mean the same thing. With a multiplicity of 3. But let's talk about why that occurs. We haven't talked about multiplicity yet this year. That was from Algebra 2. If this is the x-axis, and your graph goes through the x-axis with a multiplicity of 3, your graph would look something like this at that x value. It would behave in a somewhat cubic fashion. And it could actually be a multiplicity of 3, 5, 7, 9. It doesn't have to be just 3. It's any odd multiplicity that's not a 1. Because it'll go through in a wiggly fashion, like a cubic. So that's how we know that inflection points will happen when a graph looks like that at one of its solutions. We can also estimate a possible inflection point between 2 consecutive maximums and minimums. Essentially, go halfway between a maximum and a minimum on the x-axis, which is how we were guessing where these are. We were trying to go halfway between here and here, trying to go halfway between here and here. And that is a true guess. It's a guess. You need calculus to find the exact value. And then the third way is just actually a conglomeration of ways 1 and 2. Estimate the possible inflection point between a 0 that has odd multiplicity, like that one, and then the closest relative extreme value. The closest. Okay. Whatever. Okay, don't get bent out of shape about it. And in the homework, I'm sure the directions look like this. You don't have to say what method you used. I'm never going to test you on that. AP is not going to test you on that. So we're just going to use these skills to try to identify where inflection points would occur. I don't need us to say, I used the first method. No, I don't care. Nobody cares. Okay? These aren't official methods by any means. So let's see. This one has 1 turning point, but it has more than 1 inflection point. It would appear as though there's one somewhere around here-ish. Let's just guess and say it's at x equals 1. And then there's another one right here, because it went through the x-axis with a wiggle. Wiggle, wiggle, wiggle. So anyway, it went through the x-axis with a wiggle, all right? So I am seeing 2 inflection points, and guess what? That thing is probably a 4th degree polynomial. I know it's an even degree polynomial because the endings point up. I mean, we could try to estimate the coordinates there, but I don't really care. I just need to know, could you figure out where one probably was just by looking at the graph? How many inflection points, as everybody, you can all just shout out the number. How many inflection points do you see on example B? Only 1. I'm only seeing 1 also. Somewhere between x equals -2 and x equals +3. What's the average of -2 and +3? 0.5? So you could estimate it to be somewhere around right there. I just tried to go halfway between the 2 bumps. And since AP is not going to ask you to estimate that value, I may or may not put it on a test. And if I do put it on a test, I'll be pretty lenient about where the estimate is. as long as it landed somewhere close to the middle. You know what I mean? And this last one is an awful lot like that, isn't it? It's just upside down. So it will also have 2 inflection points. One halfway between -4 and -2-ish. Is it guaranteed to be halfway? No, but it's a great estimate. And one somewhere halfway between -2 and almost +1. Was that like -1/2 or something? So like here-ish? I don't know. And I'm very happy that I was able to finish that example, because that leaves us with the last page that we will tackle after the nice long weekend. I say we call it there.